那我们开始吧。So 我们上次我们开始学习技巧模型。技巧模型的特长是具有有限个场景场minimum model。So we start talking about minimum model 技巧模型。So this has the finitely many primary field. Okay. 然后什么？OP is closed. Okay. 所以我们严格的计算关联函数，然后central charge has fixed volume. I mean central charge 中心核是is the rational number. So 有例数。So those are the 技巧模型的特点。So 我们So 这次课我们学到这些特点。Then we're talking about the cost determinant. We're talking about the cost determinant. To derive this property, we start talking about the cost determinant. So what is the cost determinant? So it's defined by each level. Defined by each level. Level means starting from the primary field. Primary field we act as the Pirasol negative mode. That's level 1, level 2, and so on. So at each level one can define in such that the cost determinant is the what kind of expression I use for cost determinant? So G N lambda. Like this. So where the mu, the number of box of lambda is equal to n, So dimensions. So last time, so given a Young tableau or like the partition. Like this way, so that is like this way. This is lambda 1, lambda 2, lambda 3. Number of boxes like this way. That is the that's my definition of first recall. Like this way. This way. And then, so the absolute value is the number of boxes on Young tableau, which is n. So this is level n. Cuts determinant or cuts it's Shapovalov. I mean, for Pirasol case, cuts determinant is more appropriate. For the other cases, for W, anyway, I'm not going to say anything. W algebra. But anyways, sometimes it's called Shapovalov determinant. So that's the case, and then so last time. So last time we computed the level 1 is super easy. Level 1 is the H, L1, L-1, H, and so on, which is just H, as far as I recall. Was it correct? 2 times H, most likely. I don't remember. Something like that. And then we also computed, so level 2, or level 2, it's a 2 by 2 matrix, like this way. Yeah. I forgot how to say in metrics. Metrics in Chinese. How to say How to say metrics? 矩阵. 2 by 2 矩阵. Okay. And then we can. So this is the G H. Okay, that's G. And then we can take the determinant of this matrix, or no, 矩阵. So that is for Katz's determinant, and then level 2 case is given by 32 H minus what's that? H12 C and H minus H21 C. Okay, and then H12 to 1 is given by 1/16. Like this. Full side. The part technique. That's it, just fine. Okay, so therefore, if the given the central charge C, and if H is equal to H12, so this primary field you start with H. Start with it has H12 or H21, which means that the determinant is equal to 0. So determinant equal to 0 means that if eigenvalue must have 0. Okay, eigenvalue of this matrix, it has to be. So this is symmetric matrix, so it can be diagonal as well. And then eigenvalue. So when this the primary field has a particular value, it has the 0 eigenvalue. That's what. Okay. Okay. So 0 eigenvalue means what? So this means that so if you have the something like it's the so here, so this means that the H, so I will explain what it is, L minus 2 plus A times L minus 1 square acts on H. Okay. So this has the somewhat corresponding to eigenvector for zero eigenvalue when the H takes this kind of value. So that's the case. We can just have the following thing. Okay, so for instance, okay, so suppose you have this, let's call chi. Okay, and then this chi has a zero eigenvalue means what? So this means that even if you act as any zero eigenvalue, chi itself has to be zero. It has to be zero. So this has to be zero. And also, moreover, if you act anything, any state on in this Virasoro, so the conformal family of this one, you will get zero. So that the chi with any state which can have lambda h has to be zero. So this is the property for this kind of zero eigenvectors, zero eigenvectors. Okay, so I will explain. I will derive this A by using. I can use this property. So this chi is called nu vector, or singular vector. So this is the definition of the nu vector singular vector is that it's inside. So the definition is inside. So there is a chi in the boundary module. Boundary module on C and H. This is the boundary module. We're given a C and H. So which means this one. Which means this one. So boundary module. So this is called boundary module C and H. So C and H is like this. So therefore, it's an infinite dimensional, infinite dimensional vector space. And then, so this chi has a following property. So it's also not any state in the boundary module is equal to 0. So any state in boundary module. Which means that any state in boundary module can write down like this way, lambda, and then h is equal to 0. This means that the chi is analyzed by any n, where n is greater than 1. So this is the definition. It can be treated as a definition of the state inside of a module. So. Okay, so that's the case. So let me derive why. So when this central charge is whole, one can construct such a state. Okay, let me show you how to derive that. Okay. So at the level of 2, so any state can be written in terms of linear combination of this L minus 2 and the L minus 1 square acting on this. And we can use this property to derive this one. So therefore, since the L1 acts on chi is equal to 0, means that you can take L1 and then L minus 2 and the computation ratio on A acting on H and the A times L1 acting on L minus 2 minus 1 square and H. Okay. And this one is equal to, if you do Virasoro algebra, so what would you get from this computation ratio? So computation ratio L1 and L minus 2, what would you get? Thorough algebra. Do you remember? What do you get from computation L1 and L minus 2? Okay, good. 3 L minus 1, good. And A, this will require a bit work, but you can write down this one times 2 times L0 plus 2 L0 to L minus 1. And then if you write down everything, this will give you. So L0 only see the L0 acting on the state is H plus log. So therefore, one can write down this is 3 plus 2A, 2H plus 1 acting on 1H. Okay. So from here, 2L0 will give you get 2H. And then L0 acting on L minus 1H is the 2H plus 1. Fine? So that's how it works. 2H plus 1. Okay, good. So this is a state. And this should be equal to 0. This should be equal to so therefore A is equal to minus 3 to 2H plus 1. H has to be like this. Okay. So furthermore, so one can do the following exercise. So here, so far, we understand that this linear combination, value of linear combination of A. Okay. Now we want to relate the H and C. How H and C are related? Because this roughly is in order for no. So what we learn from Cauchy determinant is that H has to take particular value, H12. Okay. So to do that, we use the fact that the next is the you use L2 chi equal to 0. Then we can use the following computation relation. We know that this L2 and L minus 2 will give us some central charge. Because I mean, thorough algebra always. I mean, I hope at the end of this lecture, you can write down. It's called anyway. 被写那个比如说代序 C over 24 and square minus 1 delta n plus m. So n plus m equal to 0, you get the sum central charge. Okay. Therefore, from here you can get the sum central charge. Okay. So dependent central charge, and at the end of the day, so this has to be 0. Will give you that the central charge should satisfy the following: 4h plus c over 2 plus 6ah is equal to 0 from this property. So if you do the honest calculation, you get this. So now you can plug this one into here. One can see the relation between H and C. And it turns out that this is exactly equal to this one. This is exactly equal to this one. Okay. That's what you get from this analysis. Okay. So therefore, so at this Cauchy determinant equal to 0, Cauchy determinant equal to 0, so you get some new vector for this kind of vector. You will get. What's nice about this new vector? The question is, and then I think I should talk about a little bit about. Okay, what's nice about this new state? New state. New state of singular vector. What? Okay, maybe new state. I don't know. New state. what's nice about this null state is that one can use this property of null state to determine 关联函数。Okay. So there is state operator correspondence, right? 态双符应对应 state operator correspondence will tell you that there is some operator, whatever it's z, I call it. Okay, z, like this. So the null vector or singular state, singular vector or null state, this property will tell you that so this property, so the important part is this null state is orthogonal to any vector in Bernoulli module. Any vector. So given the vector in the Bernoulli module, given the vector in Bernoulli module, it is orthogonal always. This is orthogonal. This property is a whole. So this means that in the correlation function, it always have this correlation function must have vanish. Whatever, phi 1, c1, phi n, cn, it should be 0. Because I mean, chi always analyze vacuum. Because the chi always analyze vacuum, and it just orthogonal to any primary fields and so on. But this one is indeed equal to the, let's consider H corresponding to some primary field phi of z. So this is primary. So 储气场. Okay, 储气场. So this one can be understood as following the differential equation. Acting on phi of z, phi 1 of p, 1, like this. Okay, so our purpose is to determine the correlation function on primary field. Okay, primary field. But this correlation function on primary field, if there exists such a null state, this means that that will give you some differential equation. So null state exists particular body of H. Okay, particular body of H, written in terms of central charge. Okay? So in the case of level 2, this is the body, has to be. If this is the case, the correlation function, including its primary field, satisfies this differential equation. This one's the first found by Delap in Purekov technological. Delap, this is called BPC equation. BPC equation. BPC equation, yeah. But it's a differential equation. Because we already knew that how L minus 1, L minus 2 and acts on the primary field. That's we already see by using T phi of B. So if you write down this one, so you can just write down this one is as okay. So this one last time for the 上次课我们学到了，已经学到了，所以如果你就不明白的话，你要复习下次的内容。Acting on is correlation function. Acting on correlation function. That's that's what we learned last time. So Yes. So L minus 1 always give you just first derivative. It's called derivative is called 倒数, right? 倒数. Yeah, anyway. Derivative, and L minus 2 is coming from here. It's T phi OP. So this is, you can easily see, right? So T phi OP, phi I Z I is always HI phi and Z minus ZI square. And then del phi Z minus ZI. That's OP, right? And then this is exactly the OP you can see. Okay, so this is a differential equation you see. Okay, you can obtain. Okay, fine. So therefore, if you have this kind of particular value of, if you have particular value of this, the conformal weight, parameter is conformal weight, one can, the correction function is highly constrained. So this will give you, so this will give you the constraints on correction function. So that's why. So this analysis of a Katz determinant is very important. Okay. So this is level 2. This is level 2. Let's go to higher level. So if you go to higher level, so if you go to higher level determinant. So this is the determinant of G and H, with some central charge has the following number. So there is some overall factor H minus H or SC and P and minus or S R and S less than that. Okay. So this is kind of like an expression used. Okay. So this P is the partition. This is already partition. Number of partition of n minus rs. Okay. So P2 is either 2 or 1 plus 1. So therefore, 2 is equal to 1 plus 1. So therefore, this is 2. P3, okay, let's do the non-trivial. P4 is what? 4 is equal to 3 plus 1 plus is equal to 2 plus 2 plus 1 plus 1 plus 2 equal 1 plus 1 plus 1 plus 1, so 1, 2, 3, 4. This is 4. Oh, okay. Am I missing something? I think that's it, right? Is it correct? I hope I'm correct. Anyway, so that's partition. So here the true how to say, conformal weight or no vector is really R S is equal to capital N is the level N. Will tell you that the null state. Null state. So existence when HRS with this number, then you get the true null state. Okay, so that's the so if R and S is less than n, not equal to n, that is coming from the how to say lower level null state. For instance, if you look at this determinant, this H this H really comes from the null vector from level 1. Okay. Null vector of level 1 is vacuum. L minus 1 is equal to B. It's equal to 0, right? So that's it. So this is a null vector. L minus 1 vacuum is coming from here. So if the compound weight is 0, which means vacuum, will give you this H. This is essentially H minus 0. Okay? H minus 0. So this factor is really coming from lower level 1 null state. Likewise, even if you go to level n, so that all the lower level null state will contribute to the determinant, Katz's determinant. But the true level n null states can be found when r times s is equal to n. It's called r times s then u n. Is it correct? Okay. Only that case level n null state can be picked up. Okay. And if you do the so this one is done by before BPZ, 1979 by Katz. And then this one is given by, I mean, there's a few expressions one can write down. HRS C is equal to H0 plus 1/4, like this way. And I will write down what's H0 and R plus 1. Okay, so then H0 is equal to 1/24 C minus 1, and R plus 1 is given by this number, 25 divided by square root 24. Okay, so that's the okay, so that's the expression for level n. Given the R and S, you can have this compound weight for expression. Another expression one can have is as follows. This one is become very important at the unitary minimum model. Unitary minimum model is called, I already forgot. The unitary is 单位心奇小模型. Anyway, unitary minimum model. How to say unitarity in Chinese? Huh? 遥正值. Okay. It's okay. Okay, and then I learned something good. Okay, anyway. Something wrong. Unitarity is the p plus 1. R minus p minus s. Oh, sorry. P times s square. P minus 1. So when C would take this value, so this value, this is the central charge for unitary minimum model actually. Then the compound weight for that give rise to the null state is in fact this number. That's another expression. It's a different way of expressing. I mean, here H is given for any central charge C, but this expression is particularly useful for only unitary minimum model. Minimum model. Good. Any question at this moment? I mean, here I assume P is the integer for P. Okay, so P is integer, is a unitary integer or positive integer, is a unitary minimum, in fact. But here P can be an arbitrary, like an arbitrary number for R. Then you can adjust the central charge by solving this equation. Right. So that's the case. Okay. So that's the case. And then I can write down this. I think. Okay. So I think I can show you one mathematical file. So I forgot to record. Sorry. Sorry. So now the first half an hour is missing. Okay. Anyway, so let me show you. So before the couple of announcements. So I add a problem 4 in the homework 2. So I know like many students, okay, I would say like more than 30% of students already submit the homework, but please solve the problem 4. I add a problem 4 for minimum model, just derivation for today's content, and then resubmit. The deadline is a week later, so it should be okay. So that's one thing. Another thing is that I add a mathematical file. So let me share screen. How can I share screen? BG pen. Okay, fine. Let's see. So is it better to turn off the lights? Better. Slightly better. So first of all, I forgot to show you this conformal transformation. Conformal transformation is the 2D conformal transformation holomorphic one. So this is a grid, and then this is like I should show you like a first lecture or second lecture. So this is the plot for z goes to z square, t square case. This grid become lattice become like this way. So that's the. But at each intersection is the orthogonal. So that's why it preserves angle. Anyway, and here it should be 1 over z. 1 over z is something like this way. So line becomes circle. Anyway, so you can just play around. So this is z's absolute value square. The absolute value. So it involves this what was that? The anti-homomorphic one. So therefore, this does not no longer preserve angle. That's the conformal transformation. Anyway, so this kind of thing can be programmed easily by using Mathematica. And I already put this Mathematica into e-learning, so you can program. And another thing I wanted to show is what was that? Oh, minimum model. I think is this the one I wanted to show? No. Cuts determinant. Okay, good. So this is the computation for cuts determinant, Mathematica. So I just import some Birasara algebra, so how to compute that. Anyway, so as you can usually see, m minus n times blah blah blah, c times c over 12 times m squared minus 1. So this is just computation relation of Birasara algebra to compute cuts determinant. And I just put it into the e-learning, so you can just play around. For instance, this is cuts 2 means the level 2 cuts matrix. And this is the matrix. Level 3 is something like this one. Okay, level 3 is something like this one, and so it's like this way. So you can just compute as you want. Oh, sorry. As you want, like, and then if you want to compute determinant, you can easily compute, like for instance 2, and that will give you this kind of, and then for instance this is factor or something. Anyway, so this kind of like you need to solve, and you need to solve this one to get the correct number. For instance, one can just show that the solve. Sorry, solve. Is it hard to see? Is it hard to see? Is there any way to make it bigger? Anyway, solve this one is equal to 0h, and you can have the solution. I mean, this kind of stuff you can easily do that by Mathematica. Maybe anyway. So how can I make it bigger? Oh, this is bigger. Anyway, so that's what I did. And the cut determinant, the expression I show you is just now given here. And then, anyway, so you can play around the Mathematica and so on. So H21 is something like this one. Anyway, so you can H13 is something like this one. So it's a body of it, weight that gives rise to the level and no state. And you can plot. You can plot in terms of this vertical axis is H, the horizontal is C, and this is H12, and this is the H13, and so on. H1 and so on. H12, H21, H13, H12, and this is H22, and so on. So these are curves. When central charge is C, given the central charge C, you have a two body for H that give you two body of H that give you this conformal weight for minimum the null vector. Anyway, so those are, you can just play around and then write down the anyway, so you can play around and in Mathematica one can just write down draw the picture or figure for this conformal weight and so on. It's just it's a good exercise to be familiar with Mathematica. So if you're interested, you can just play around. I mean, it's on a e-learning, or I already put it. Yeah, so that's thing. And we will see that so these are curves for this HRS. I wrote somewhere around here, HRS, here, HRS here. So these are curves for here. And then here, it's always, this curve is always become real when the HC is equal to less than 1, okay? Less than 1. This curve up here, only C is equal, central charge is less than 1. Okay, and then but C is greater than 1, curve does not involve anything. So therefore, and as you can easily see, so H is the H. So cut determinant is H minus HRS and the product, right? So therefore, once you cross this line, so H, when H is some particular on this curve, this cut determinant becomes 0. Okay, but once you cross the cut determinant, changes sign. So like for instance, like a plus minus plus minus plus minus and so on. So once you cross the the curve of this HRS, you will get the cut determinant change the sign. On this curve, cut determinant equal to 0. So this is so the change sign is that there exists such a non-unitary states, so negative norm states. So 그 다음에 you just have the inner product with states and take a determinant. You get the negative, means that there must be some negative norm state once you have a cut system. Therefore, this region is all in fact contain this negative norm. And here, this curve contain the null state. That's okay. Null state existence null state does not harm the unitarity and so on. Unfortunately, most of the curve, most of the point in the curve also have a negative norm state. If you do the careful analysis, only part that has do not have the negative norm is this point. When this the curve next to each other, it just intersect. This point become like a unitary theory. Some only special point that intersect two curves becomes a unitary theory. So that's the analysis the BPC did. So that's the case, and I have to explain a bit more about the BPC story. So any question at this moment? Okay, so this one is the conformal weight tensor. Okay, that's I can show it later. Okay, so that's the case. Okay, that's okay. So if the Bernoulli module, so this on this curve, the one module B, C, H, or S has a null state. This means that the one module has a representation. So B, C, H, R, S is called reducible. Reducible as a representation. It's not irreducible representation. Reducible representation. So to get the irreducible representation, so irreducible representation can be obtained by just quotient the module and throw away all the null states, which is C, H. I just suppress RS. I mean, if you want it, RS, RS, RS. And this guy is the all null state. Okay, so that's the case. So if chi is known, so it's this one is also known. If chi is known, means that even if you act whatever there are some mode on chi, it is also known to the any orthogonal to any so orthogonal to any state. So the type psi is equal to 0 means so therefore this one is also 0. This means that this one is also 0. Any state of psi in Berg module is orthogonal. It's actually orthogonal. That can be easily checked by computation. Yes. For instance, the L1 acts on L minus 1. So L minus 1 of chi. If you do like this way, and then this means that the what was that? 2 times L0 acts on chi, and this is the I'm doing something stupid. No. Let me think. Okay. I'm doing something stupid. Sorry, I got confused. Oh yeah, sorry. I'm very sorry. I made a mistake. So there's a clear difference between singular vector and null state. Sorry. So null state means that the null state is chi. Chi is equal to 0. So this is null state. Sorry. Null state. This is null state, and then L0 chi is equal to 0 in Berg module for n greater than 0. Okay. So and then singular vector is the chi is not primary. And this is called singular vector. Sorry. It's called singular vector. So it's a different thing. It's a different thing. Singular vector is always null. So what's important is that the null state. So the null state inside is very tiny pieces. The tiniest piece is singular vector. Sorry. And this is the singular vector. The tiny piece. Okay. So yeah. So that's the meaning. So for instance, so L minus 2 plus A L minus 1 squared H. So this one become a singular vector chi. So this singular vector chi, when A is particular value I showed you before, and the H is particular value. I already forgot what are those. So okay, let me sorry. So chi, so this chi is L minus 2 H plus A L minus 1 squared H, and when H is equal to H12 or H21, and A is equal to minus 3, like this one, then this guy is singular vector. Okay. But L minus 1 chi is not singular but null. It's a null state. And of course, singular vector means that it's inside a null vector. So it's a singular automatically means null, but null does not necessarily mean singular. Okay. So this is null state. This is null state. Because we know that the chi square is equal to 0. Okay. Then L minus 1. So that's what I want to show. L1 and then chi is equal to 2L0 chi and chi, and this is equal to 0. H. This is equal to 0. So therefore, null means that the null is just the inner product is equal to 0. So therefore, this like. Sorry about. So I just make you confused. Okay. And what's important is that the given a null state, its descendants are all null. Okay, given a thing. Okay, so therefore, if you quotient by all the null state, so if you quotient the Berman module by all the null state, you get the irreducible representation of the Birasoro algebra. That's how you get the irreducible representation of Birasoro algebra. Fine. Okay. So that's how you do that. So this is the irreducible representation. This is the irreducible representation. Oh. Okay. Irrep of Birasoro. So algebra. Algebra. Isn't some mistake? Is there some mistake? Is it okay? Okay, that's the case. So now how we can use the BPC equation to determine to minimum volume. Okay. Fine. So let's recall BPC equation. Now, for instance, so this HRS. Let's write down this one. Is by state operator corresponds to phi RS of T. Okay. So that's the state operator correspondence. And if you start with the primary field at the level R times S, there is a null state. Okay. So the Cox determinant will tell you that the so in Berman module BCHRS has the singular vector at RS level. Okay, at the level. So that's the one we know. So in particular, if you consider phi 1, 2 of Z, and then X, and this will satisfy the BPC equation. Sorry, I need some space to write down. repeat the equation. Phi 2, 1 or phi 1, 2, whichever is okay. X, and this will satisfy the following equation: L minus 2 minus 3, 2 times 2h plus 1, L minus 1 squared is equal to 0. And this will give you the some differential equation, just a repetition of what I wrote just before. Okay, so that's the case. So x is the phi 1 c1 phi n cn all primary product of, it's a product of primary field. How does that product in Chinese? The name product of primary field. Okay, and then we already knew. So we already knew that the two-point function. So we know that the two-point function or 1, 2 or phi of w. So we know the form of two-point function. So this one, okay. Anyway. Another conformal invariance is called 光性变化的不变性 would determine this two-point function, and that will give you similar ci, and then 2h 1, 2 divided by some constant. Some constant. That we already knew. And here we already know that we are only doing the homomorphic one, so it's this one should be okay. Okay, and then just write down in terms of this, and then here it should also, this compound dimension is h1. It should be. That's a requirement of this requirement of the two-point function to be non-vanishing. Okay. Sorry, is it the 2 times h1, 2? Is it correct? You guys already knew, right? It's 2 times, right? I think it, or not. I don't remember. I should have known. I think it's okay. It should be okay. Yeah. Because for instance, in free field, what are the compound dimension of this one? 1, right? And then if you consider this one, what's this? What's the power? 2. So these are primary in free field, and 2 times 1 is 2. So this should be okay. This should be okay. So this is a two-point function. Okay, now let's see whether this one will satisfy this equation. Okay, will satisfy this equation, and you can easily see that this 1 minus z minus ci c1 So, and then this phi. Okay, anyway, so phi 1, 0. You can, so this is a good exercise to check. So this is exercise. So this identity is exercise. Just plug this one into here. Whether this equation is satisfied. I mean, that's you can easily do that by mathematical and so on, or you can do the calculation by yourself. Which I don't want to do. I mean, it's not so difficult. I think it's not so difficult. Yeah, it shouldn't be so difficult. Anyways, I think it's better not to do it now. I think if most likely I will make a mistake. I mean, it's just plug this one and do the solve the differential equation. You get it. Have a 3-point function. 3-point function. The 3-point function will tell you something very, very non-trivial. So that's an important thing. We know that the conformal invariance will tell you the 3-point function has a particular form. Okay, so particular form. So 3-point function is satisfy the following the symmetric form. So 3点函数 will satisfy no. It's something like this. And like this. So this one is derived by using conformal invariance. Okay. So, but we can just suppose this phi is the phi of z is really phi 1, 2 z, then h is equal to h12. Suppose this is the case. Then plug this one into this BPC equation and see what's going to happen. And this differential equation, so this differential equation, you can just plug this one into here. And this is only satisfied, BPC equation is satisfied only when, and this is very important, only when the H2 is a function of H and H1. I'm not going to write anything. So this one is already written in the lecture. It's a function of H, which is H12, and the H1. H12 is some analytic function of the H and H1. Okay. So otherwise, so this means that this is no longer satisfied mention that unless H2 is not valid, so this structural constant needs to be 0. Okay. So the 3-point function is not well defined. So this is the whatever H, H1, H2, whatever you call it. Anyway. So this structural function is non-vanishing only when this condition is satisfied. This one is my lecture note online in 5.28 in current lecture note. Anyway, so all the lecture note. I mean, do you want me to write down the full expression? I mean, I can write down, but it's It's just long. I mean, I can write down the full expression. 1/6 plus h over 3 plus h1 plus minus 2/3 square root h squared plus 3h h1 plus h over 2 plus 3h1 over 2 plus 1/16. Anyway, it's not that bad. It's not that bad. So the BBC equation, so when this particular conformal vector, particular conformal parameter is involved in three-point function, because of this BBC equation, so we know that two-point function vanish when two of the conformal weight are different. Unless the conformal weights are equal, the two-point function vanishes. But three-point function, we didn't have such a constraint before. Before, we didn't have such a constraint. So people just mentioned that the conformal imbalance we determine is form of three-point function. It's similar form. However, in the case of this particular conformal weight, which provides a null state, the three-point function of the conformal weight has some constraint. It's h2. It's some function, which is written here. It's the relation between h and the h1. That's the important thing. So this will tell you some OPE. So this will tell you some OPE information. OPE information among 5 RS. Okay, before going that, let's take a break. Yeah, so before going that, let's take a break. Yeah, so this OPE, I will do that after the break. Okay. So any question? Okay, if not, let's take a break, 10 or 15 minutes. And you should tell me this Chinese 中文词汇. What's that? So the matrix is Juji, right? How do you write that? I forgot something like and then James. I don't remember how do you? Huh? Anyway, you should come and write that. How is the product of primary field? Product is 前进 前进 something like this one. 前进 前进 okay. 距离长的前进 Anyway, let's listen. Yeah, 我们休息吧，休息一下，休息一下。So unitarity is, how to say unitarity? Huh? Yeah. Can you write them? 遥见系技巧模型。OK， 遥见系。啊？有见系。有。OK。
It is translated from its pronunciation.
I see. 有技巧模式。
Just in Arabic.
有。OK。有。有。强。OK， 注强。注强。正 ，OK， 正。Can you write down how do you write down 绩效？有绩效模型 like this one. You cannot say. Unitary minimum.
I don't know how to translate. Maybe it's called 腰正绩效。
腰正型。
Because for unitary matrix, we call it 有矩阵。unitary matrix.
有矩阵。Okay, thank you very much. It's a good. I also Chen. Yes.
Yeah. Introduce units. Okay. Introduce representation. But where will you be the usable or reusable? Or just give an introduction?
Because so given the most singular vector chi, you can have you can act lots of Viraswara representation, right? You can from here you can just also create the Berman module.
Yes.
So Berman module. So this is also some representation of Viraswara. So it's a sub-representation inside of Berman module. So this chi is L-1 or L-1 square and so on. Chi. This is new vector. Or singular vector, sorry. Inside Berman module. Inside Berman module. So Berman module starts with some H or whatever HRS, and they just act lots of the Viraswara mode, negative mode. And at the level R times S. So you will hit some singular vector, right? And from there, you can further act on Viraswara mode, right? That will give you sub-representation. This is sub-representation. Yes. Sub-representation of Viraswara. So therefore, it's no longer irreducible representation. So if there exists a sub-representation, it's no longer irreducible. So you have to throw away this one. I mean, why? Why we need it? Because I mean, stress energy tensor, quantum mechanical, we need to treat this one is the the stress energy tensor is the current of conformal transformation. And then, so if you consider the whatever OPE of this kind of stuff, correlation function include T, definitely it has to involve the center charge. I mean, even quantum this kind of thing happen. I mean, it actually just classical transformation or classical. But I mean, C can be understood as a anomaly. Yeah. So it's some quantum classically true, but the quantum mechanics not true. It's called anomaly. So there are lots of anomaly appear in quantum physics. ABC anomaly, many things. So this C can be treated as an anomaly. Yeah. Yeah. So in quantum mechanics, you have to consider Virasoro algebra instead of the Witt algebra. 那我们继续吧。So， 我说到有一个问题啊。So verbal module. So is verbal module reducible? I mean, if you start with HRS, and the verbal module is something like whatever L minus 1 HRS, and then L minus 1 square HRS, and so on. So this is a verbal module. I call it this is B, CH, HRS. And then at the level of R, here level is R, S, you encounter some null state here, or singular vector, singular vector here. And then from there, one can just form L minus 1, chi, and so on. One can just Birasol, negative Birasol mode can act on chi. That will create all null state. That will give you the subrepresentation of Birasol algebra. Subrepresentation of Birasol algebra. So if the representation contains the proper subalgebra subrepresentation, that's called reducible. So one can quotient out this subrepresentation to get irreducible representation. Okay, so that's the anyway. Fine. So now, so we understand that if you have the primary field with particular conformal weight, then the three-point function is highly constrained because of BP's equation. Now, what if H1? So this is H is equal to H1, 2. So suppose phi 1 of Z1 is phi RS, where H1 is equal to HRS. Okay, so then it turns out that H2 can be HR S minus 1 or plus minus 1. Okay. That's the case. So this, depending on plus or minus, you get that S plus minus. I think it's opposite, minus plus. Minus plus. If you just consider plus minus, it's a minus. Okay, so that's the wait. So this is positive, so it should be plus minus. It should be okay. Sorry. Okay, that's the how you get the. It's a very particular thing. So suppose H is H1 2, and H1 is HRS. The H2 has to be also this conformal weight. Okay. So somehow, so this will tell the OPE 1, 2 between RS is the phi. I think I don't need it. Phi R. This one is 1 plus phi R. This one is 1. Okay. So that's the. So OP between the some primary field with particular conformal weight given by this solving cuts determinant equal to 0 will somehow the OPEs will give you another primary field that satisfies this H some particular condition. Okay. So similarly, if you just change this is 2, 1, phi 2, 1, and phi RS. Then this one is the, as you can easily guess, like this. Okay, it's on the cross under. And in particular, so we can have the point. Like this way. So now this is the OPE between this primary field under this OPE with this primary field H12 and H21 can be understood how to say ladder operators. I mean, maybe this can be understood lowering operator, this is raising operator in terms of S. Whereas the phi 21 is the lowering operator or raising operator in R direction. And more generally, if you solve this BP's equation, then one can form the following thing. So phi R1 S1 plus phi R2 S2 is equal to sum over phi KL, where K and L satisfies some condition. I'm not going to write down everything. Some condition. So this is the consequence of solving BP's equation in 3-point function. Okay. 3-point function. So if you apply this BP's equation to the 3-point function, you always get this kind of constraint like this way. You always have this kind of constraint. And if you plug this HRS formula into this constraint, you always have this kind of relation between. This time condition means that if you want to understand the time condition, it's written in 5.30 of my old lecture note, of the old lecture note. Okay. So this means that there are infinitely many primary fields labeled by two non-negative, two positive integer R and S, positive integer R and S. These are closed under OP. Okay. So far, we haven't said anything about the minimal model, but if you just do the analysis of this, whatever, urbanization Virasoro algebra, one would reach to this conclusion. So if you have a primary field with the HR, or conformal weight is given by, I don't remember, H0 plus 1 over 4, R alpha plus S alpha minus square, as far as I remember. Conformal weight. If you have such a infinite many family of the primary field, they are closed under the open. That's the important problem. Okay. So far, but however, so what we want is that this, how to say, find many primary fields for minimal model. Find many primary fields. So 有限个处技巧。To have this finiteness, we need to somehow adjust. We need to adjust the central charge and so on. So that's the thing we have to do. We have to adjust. So far, there's an infinite family. So this is the S direction. This is R direction. And we know that the primary field this is 1, 1. 1, 1 is actually back here. 2, 1. So there's a lattice is like this way. Okay. Lattice become like this way. Okay, and then so at each point we have, for instance, this at each is 1, 2, 3, 4. 1, 2, 3, 4. Okay. So here, for instance, this one corresponds to 5. What was that? 1, 2, 3, 4. 4, 3. No. 1, 2, 3, 4, 5. Okay, 4, 5. Okay. So at each lattice point corresponding to some primary field with some particular conformal weight given here. Okay, that's the case. And then so recall that the R plus and R minus are all written in terms of the. So as you recall, R plus minus is given by some central charge. C minus 1 minus C plus minus 25 minus C divided by 4P and then P plus 1. So, this is square 24. Sorry, square 24. 24. Okay, and then so assume like a C is less than 1. Let's assume C is less than 1 for so this assumption. So if C is less than 1, and then all the conformal weight can be just derived at the as follows. So tangent theta is given minus alpha plus divided by alpha minus, and theta is something like this one. What was it? It's hard to draw. Something like this one. This is theta. This theta, you just write it down like this line with theta. Is tangent theta is given by like this way, and then so at each primary field you just project to the shortest distance. Okay, shortest distance like this called delta. Okay, and here and the primary field phi rs is given by h0 plus 1/4 delta squared alpha plus square plus alpha minus square. That's delta is the distance between this line, yellow line, from this the lattice point. And in fact, if you do the simple calculation by using this formula, so delta can be understood of R alpha plus S alpha minus absolute value alpha plus square plus alpha minus square and square root. That is the, you can derive this one very easily. If you can, anyway, 因为好像复旦大学已经this one is too easy, 太容易. So this delta is the just distance, and if you plug this one into here, you get this one. Okay. The important thing is that for generic C, this theta is the this angle is irrational, which means that it never hit the point, okay? Hit the lattice point. But some particular value of the central charge will get the particular value, so for instance, so when C is equal to the following things, so 1 minus P prime square 6 times PP prime. Sorry, so 6 is the overall function here. Well, P and P prime is the natural number. So then, so particular number. What I'm trying to do. 1, 2, 3, 4. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Am I drawing correctly? Somewhat strange. Yeah, this cannot be happen. Cannot happen. So, most likely something like this. So this one is the P is equal to 4 and the P prime is equal to 5. So this is S and R. So if C is this particular value, this line, this Sayer, somehow is tuned in such a way that it hits the P and P prime. P and P prime. More precisely, P prime. They satisfy this following equation. Okay. So they satisfy this condition. So that line hits this lattice point. Okay. If this is the case, we have a magical property for conformal weight. Okay. So magical, if this is the case, the consequence of this property is that the HRS is equal to HR plus P and S plus P prime. Okay. So this is super easy to see because so the conformal weight is just the distance from this line, right? Distance from this line. Okay. And if you hit this one, and then you have the same block here. You have the same block here. Okay. So therefore, if this pattern is just a conformal weight of this block is the same as this block here, and so on. Diagonally, you can just repeat the same pattern. So there's a length here is always same into the next one. Okay. So what's happening is that so if you globally, if you look at like this way, the S and R, and you have the something like whatever, it just scale down. So you have something like this block is here, and the same block is something like this way and this way and this way, and so on. It just repeat like this way. Okay. So this is a P plus P comma P prime, and this point is 2 times P, and then 2 times P prime, and this point is 3P and 3P prime, and so on. So it just repeat all the pattern. Because it's just in lattice point here, the distance is just as you can see. So the conformal weight is just given. Sorry, this is not phi, H. Okay, H. So this one is the following here. So it's just distance between this line and the lattice point. So therefore, this distance is the same as this distance. Okay. So therefore, this pattern is just a repeat in the how to say, along this line. Okay, along this line. So that is this property. Furthermore, if you just plug into this formula, you just see that they plug this central charge into the formula. You just realize that the HRS is given by the square minus P prime. Square divided by 4P prime. Okay. So this is the case. Then you will realize that this formula has a symmetry. So this is has a beautiful symmetry that the HRS is equal to like this property. So like this property. So this kind of pattern can be seen from this analysis. And furthermore, what's important is that the OPE is of the phi RS are closed under so R is less than P and 1, and the RS is less than P prime and 1. So that's the important property. So if you just use the 3-point function, so I'm not going to derive this one. So this is super good exercise. Exactly. So if you just have this kind of block, the block here, at each lattice point sits in some primary field, and then so for instance, this primary field times this primary field is somewhere inside this block. Okay. Somewhere inside this block. You won't get somewhere else. Okay. You won't get somewhere else. It's closed under this inside of this block. That's important. Okay. So inside this block, there are finite many primary fields. Okay? And they are closed under OP. So that will give you a minimum model. So when particular central charge appears C, like this way, somehow you can pick only the primary field inside this block, and if you just compute the OPE between them, like a phi, whatever, RS cross phi Fn, and this will give you sum of phi KL. KL is always inside this block. KL is always inside this block. This block means this block. Okay. This block. KL is inside of this block. And also, OP is closed under this block. So that's how we get the minimum. So the important part is that when you choose central charge C, this line, this alpha plus the ratio between alpha plus and alpha minus times negative sign hits some last point here. In that case, one can pick. So this pattern will show up, and in fact, one can just only use the primary field inside this box. And in this way, one can obtain the minimum model. Fine, and then I can show you one thing by Mathematica, okay? Okay, just a moment. I think I should make it bigger. Right? Okay, good. Now it's more visible. Fine. So here I just use this. The formula which is hidden behind is to list the HRS. So this is H11, H12, H21, something like that. H12, H21, H22, H31, and H32, and so on. Okay, fine. Yeah. I think I told you the wrong thing. But anyway, so yeah, I think strictly speaking, sorry. So when this yellow line hits to the point, hits the point here, okay. So this block will repeat. That's what I mentioned. And then that's you can see. So this is a real block, you can see. And this block is just, you can translate like this way. And so 0, 1 half 5 over 3, 0, 1 half 5 over 3, 16, 1 over 16, 1 over 16 is 35 over 48. 1 over 16, 1 over 16 30 over 6. So this block is the same. And you can do the same thing for the next way. So if you just make it bigger, say 13 and 13, something like that. Good. And then you can see this block will continue this block, and then next is appear here, and so on. You can see. You can easily check diagonally, it just repeat. And the important thing is that I think I made a OBE. This part is not relevant. Sorry, this part is not relevant. Only you have to look at the OBE, except these edges. So you throw away. So let me make it less 8 and 8. So you throw away these edges. What's left is 0, 1 half, 6, 1 over 60, 1 over 60, 1 half, and 0. These primary field will cross under OB. So that's an important part. So this edge you can throw away, actually. This edge and this edge, primary field on these edges can be thrown away. And you just only look at the primary field inside. Then they fall, they are cross under OB. Fine? And then, so this is actually, I think, model case. One can do the many things, like for instance, say, 2, 5, 2, 5, like this way. If you do 2, 5, what's going to happen is what? I think this is not. Okay, yeah. So this part is the same as this part. This part. So I need to make it bigger. I think 13, 13. Good. So 1 over 5 up here, 1 over 5 up here. So this block is the same as this block. Yeah, this block and so on. So 1 over 5 up here, and then again 1 over 5 up here. And then so 2 times 5 matrix, which is repeat like this way. And you just get rid of the edges of these edges, and then 1 half, 0, 0, 1 half. This part is a primary field you need to consider. And this is actually, it's called Linear model. It's not unitary model. But this 1 half, 0, 0, 1 half, this is the linear model you can consider. And 3, 4 is in fact the Eisen model. This is the conformal weight of this on the lattice. So this is 0, 1 half. And then the property of is that as I mentioned, HRS is equal to H P minus R, and then P prime minus S, as far as I remember. Yeah, that's true. So HRS, P minus RS. So for instance, in the case of azimuth, P is equal to 3, P prime is equal to 4. So H12 is equal to H, what was that? P is equal to 3, so 2, and then 2, 2, 2. H is equal to 2. Okay, so H12 is equal to H22. I might make a mistake. I think I'm making some mistake. I think this should be P prime. P prime? No, wait. Just a moment. Anyway, then what's going to happen? So this should be 3. Yes, 3, 1. Well, this should be okay. This should be okay. So 1, 2 is the same as 3, 1, right? 1, 2 is the same as 3, 1, and then H 2, 1 is the same as the H 2, 2. Okay. So H 2, 1 is the same as H 2, 2. Okay. So that there is a typo in that action. So even like inside this box, there is some repetition. That is also, like for instance, tripod model is most likely 4, 5. 4, 5. Okay. So tripod model on the song is just a look at this part. 1, 2, 3. 1, 2, 3, 4. So this part. Okay. If you look at this block, so 7 over 16 appears 7 over 16 here. 3 over 18 appears 3 over 18. 3 over 5 appears 3 over 5, and so on. 3 over 2 appears 3 over 2. So it's just a sum of like a repetition because of this symmetry. Because of this symmetry. And then this block will again appear this part. And 0 is always a vacuum. And that will appear again and diagonally, and so on. So in this way, so if you plot in mathematics, you can see the pattern of the conformal weight, how the primary field appeared, and so on. Okay, so that's what I wanted to show. And this one is also inside e-learning, so you can play around. Okay. Fine. Okay, and then fine. Okay. So yeah. So the typo is where? Right. So I told you the typo this should be P prime here. P prime is here, and this should be not equal. Okay. So not equal, less than. It doesn't. This doesn't. This means that the primary field on this edge you can throw away. So this one is no need to consider. Well, only the primary field you consider is this one. Okay, so therefore this part should be this yellow one. Primary field is closed under this yellow line. Okay, so that's the model. So, and I call this one M, P, and P prime. M and P and P prime. So only fundamentally primary field. So what you need is the essentially primary field is P minus 1 times P prime minus 1. It should be correct. Divided by 2. So this is the number of primary field it has. So this is the number of primary field. This is the number of primary field in this minimum model P, MP and P prime. So P minus 1 times P prime minus 1 is really the lattice point of this yellow part, and this divided by 2 is necessary because of this symmetry. Okay. And now we need to consider it's called 右减式 unitality. And then, I mean, it's just a simple thing. So I showed you that there's a C here and H here. C equal to 1. There is something threshold, and there is some the curve like this way, and it requires to hit the C equal to 1 actually, like this way, and something like I don't remember the detail, but something like this way, and then something like this way, and so on. So the HRS curve look like this way. I don't remember the detail. And then this part is always uniform. So if C is greater than this part, is always unitary. Okay, C is for C is greater than 1. So this one you can easily show by looking at the cost determinant, but I'm not going to say anything. I'm not going to say anything about this part because this one part is does not appear in the minimum model. So minimum model only appear when the C and C is particular value. So C is particular value of this one. Particular value of this one. And this one is only like appear in the when this one only appear when the curve intersect. The curve intersect. That's only when only place the minimum will appear, and in particular, so unitarity. So if you unitarity only appear P prime is equal to P plus 1. This is only unitarity. So M P and P plus 1 is only unitary theory. But the rest is the non-unitary. So otherwise non-unitary. This one you can just do the very detailed cost determinant, which I'm not going to do that. I mean, it's very, very, very tedious. It's very tedious, so I'm not going to do that. You can accept this one as a fact. Okay. So unitary foundation only appear here when P prime is P plus 1. So therefore central charge is given by 1 minus, often I just write down like this. 6 over P plus 1. I just write down like this way. And then HRS, the formula here, also significantly simplify to be like this way, P plus 1. Or 1. like this way. Okay. So that's the unitary minimum one. Okay. So that's the formula for unitary minimum. Okay. Any question at this moment? Okay. I mean, so this one can be shown as follows. I mean, for instance, if you consider the following thing. If you consider so if you consider this yellow range, if you consider R0S, R0S in this yellow range, and such that the P prime R0 minus P S0 equal to 1, then so from this formula, this is equal to 1. So therefore, this H R0 and S0 is equal to 1 minus P prime square divided by 4P prime. Okay? And this is the always like this way, because I mean P and P prime are integer, right? Positive integer, and so this is the definitely greater than or equal to 1. So therefore, so when this one is equal to 1, this maybe I should write down. This one is equal to 1, this equality is satisfied. But otherwise, a different pair of P and P prime, you get the negative number. So therefore, conformative negative means that there exists such a negative normal state. Okay? So therefore, non-unitary. Okay? And in fact, P is equal to P prime, this is equal to 0. And in fact, this corresponds to, in this case, this corresponds to vacuum. So in the case of the, so let's see, when R is equal to, P is equal to 3, and P prime is equal to 4, we saw that this one, right? So 1 over 2, 16, 1 over 16, 1 half, and 0. Okay? So this 0 is exactly R0 is 0. So this place is exactly the place that satisfies this condition. And so this 0 corresponds to vacuum. Okay? And otherwise, you have a negative. Okay. Any question at this moment? Fine. I think I don't need to talk about the. I don't need to talk about this torus partition function character of the minimum model at this moment, because I didn't talk about the Montgomery partition function, so I don't need to talk about it. Then let's look at the very special case for this case, item model. Fine. Okay, maybe it's better to make a summary in that case. Summary. Summary is the summary is that the R and S So when C is equal to 1 minus 6 times P minus P prime squared, PP prime. In this case, the in this case, this line there, tangent there, is the minus alpha plus alpha minus, fits to the P and P prime point. Okay? And you consider the primary field only, so you just draw with the edges only inside the square. So if you, so the primary here are closed, form closed OP. Closed OP. And this pattern is just repeated up here in the OP. This can be just found by solving this equation. And furthermore, when P and prime is equal to P plus 1 is unitary. Otherwise, non-unitary. Unitary. Yeah, and then so there's inside here there is a symmetry phi RS is equal to phi P prime minus S P minus S. There is some symmetry. Even inside there is symmetry. Inside of this yellow. So this is a 总结. So this is a So 基小模型的总结. Okay, so that's the case. Fine. Any question at this moment? Okay. Then let's take a look at the very particular minimal model. It's called Eisenhower. Okay. So from now on, so I just we focus on the Eisenhower model. Which is the simplest minimal model. But before going to the minimal model part, I just want to say the one thing. So starting Hamiltonian. And they show Kramer's variability. Kramer's variability. And after that, so we just show the so-called Onsager exact summation. So Kramer's variability is that there is a Curie temperature Tc, temperature T, and then there is a Curie temperature Tc, which this is the which describes by Conformal filter. So this is the Curie temperature, Curie temperature, and this is CFT point. But low temperature and high temperature behave very differently. But there exists such a duality between low temperature and high temperature. Duality. between low temperature and high temperature. That is for Kramer's one. Okay, so that Kramer's one duality is the simplest duality in physics, the most important one that all the theoretical physicists should know about. So this is it's just simplest duality, but you can learn many things. It captures the essential part of what is called duality in quantum mechanics or quantum field theory. So all theoretical physics students should learn about it. So it's a very important topic. And also there is some remarkable result given by one So what we are going to do is that in statistical mechanics, what we need to consider is so-called partition function. So Boltzmann will always tell us that you have to sum over all state with the all state beta over E and EI, where EI is the all state. So that's and here you need to sum up all states so that part with Boltzmann weight, and this is usually really difficult to do. E is of course obtained by Hamiltonian. Hamiltonian is given a system, you have a Hamiltonian. Computing this statistical partition function is most of the cases it's impossible, but Asimov is still, and that was done by 1944 by Onson, which is one of the milestones in theoretical physics, and that I will explain that. And in both cases, Kramer's one and the Onsaga exact result both tell the existence of the critical temperature. And at this point, the critical temperature means that there's some phase transition at this point from low temperature to the high temperature. Both results will tell you there's something special happening at the T or TC. And that is described by this conformal field theory in minimum. Fine, so that's the I'm going to talk about from now. Fine. So let's do that. Fine. So the Hamiltonian of the Ising model is given by like this way. J and I and J are adjacent point. So this is the Ising model Hamiltonian, simplest Ising model Hamiltonian. So you just consider lattice. And at each point you just want to spin and spin down. So sigma is the sigma can be understood as the power matrix sigma c. Right, as far as I recall, it should be sigma c. Or spin up and spin down. I think. Yeah, and then all possibles. Sigma is spin up or spin down. Spin down, and you just consider the statistical partition function sum over sigma e to the minus j over kb t and then sigma j, the adjacent means sigma I and sigma j. The statistical partition function. And I set this guy. So this is plus. I set this this quantity. This quantity to be equal to k, and then so we can use the identity that the exponent of x sigma I sigma j is given by cos of x and 1 plus sigma I and sigma j times of x. So that's one can use the identity. Can you see this identity? So how do we show this identity? Okay, let's see one by one. Let's see. Suppose this sigma I and sigma j, let's see, how can I show that? So sigma is plus minus 1. Okay, sigma is plus minus 1, right? Sigma is plus minus 1. And then suppose this one is plus, what's going to happen? Is equal to cos x and 1 plus tanh x. Okay. And the 1 plus tanh x is what? And this is equal to 1 plus tanh x. Is it correct? Is it correct? What did you say? Is it cos? The cos plus sinh x. Okay, and then this is e to the x, right? E to the x, right? Is it correct? Right? I think you have to normalize appropriately. Is this correct normalization? No, it's okay, right? Okay, this is the when sigma I and sigma j is equal to plus 1. Okay, and when sigma I, sigma j is minus 1. So this one is either spin up or is spin down case. Okay. And the opposite case, or either this case, then this is minus, so therefore this is cos x and 1 minus sinh x, and this is the cos x minus sinh x, now e to the minus x. Is it okay? Is it okay? Okay, so therefore this identity is whole. Okay? So this identity whole. This identity whole. Okay, so identity is 很等式。So we obtain this 很等式。Okay, so therefore, using this one, what we get is that the z is equal to product sum over sigma, sum over sigma all possible state, and then product of I and j is adjacent, and cos k, and the 1 plus sigma I, sigma j, and tanh k. Okay, so tanh k. Okay, like this. Fine, so that's the case. So let's consider the high temperature. Temperature question. So high temperature means T is very big. So T is very big means K is very small. K is very small. High temperature is K is small. So therefore, this quantity is, I think, small, right? Almost 1. Sorry. When K is equal to 1, Tansh is what? Sorry. K is very small. Tansh is close to 1. Is it the case? Sorry. I'm too heated. So Tansh K is very small. Yeah. So Tansh K is very small. So one can take the expansion in terms of this number. So one can have the Tansh K to the R, and then sigma 1 and 1, sigma 2 and 2, sigma 3 and 3, and so on. Okay? So this means that we can just consider the following thing. So you have this has lattice point. You have a lattice point. Okay, lattice point is over there. Okay, you have a lattice point, and you just consider this kind of like closed circle, like this way. Okay, and R is the length of the circle. So this N is the sigma 1, and so in this case sigma 1, and sigma 2, and sigma 3, and sigma 4, and so on. So this is length 4. So therefore, in this case, so this expansion in terms of Tansh K is that just the length of this closed circle. Okay, closed circle. And then you can consider this kind of closed circle to compute the partition function. And then sigma I takes is a plus minus 1. Okay, plus minus 1. And 1 and 2 and 3 is the number of the edges. Number of edges which in n how to say? Number of edges which sorry. And I is the the number of line, number of line and number of line which just intersect with the lattice point. So therefore, if it is a closed path, everything is even numbered. Okay. So I mean, you can consider this kind of path. Just it's not closed path. Okay. Then so in this case, ny is equal to 1. Okay, n is equal to 1. Then, but if you sum over all possible states, means that so the sigma is plus minus, right? But if it is 1, if you have a plus and a minus, if you sum them up, you have to sum them up all states. So if it is odd, if you have a plus minus, you count them, right? So therefore, this does not contribute to the partition function. The only configuration that contributes to the partition function is the cross path, because everything becomes even in this case. Okay. So therefore, this will become. So this, but at the high temperature regime, this will become 2 times cos k times n times m, and sum over p, and Tansh k length of p, and this p is a closed path in lattice. Okay, so p. So this n and m is a number of sites. This the n is whatever vertical number of sites, and then m is whatever horizontal number of sites. N times m site, in total. And this is the high temperature regime you can get. Now, low temperature regime, what's going to happen is much more simple. So this is the low temperature regime. So low temperature regime, we know that everything is aligned, almost aligned. So if you consider that the configuration is that always they want to align like this way, and the other part is something like this way, and they want to align like this way. In low temperature, so this is the low temperature. Okay. And then you can have a dual lattice. You can have a dual lattice like this way. So this is dual lattice. And then you notice that only the part that contributes the partition function non-trivially is that this. It's better to use the other color. This part. Okay. So inside this purple one is spin up, the other part is spin down, right? So therefore, only this purple part will give you some contribution to which is negative into the Hamiltonian over there. Because spin up and spin down, if you have spin up, spin down, you have a negative contribution, right? Or like excitation to the Hamiltonian. Okay. So therefore, what we need to do is that the partition function of the low temperature regime is just E2 times E to the n. This is just normalization, and sum over PD. PD is the cross path in the dual lattice, E to the minus 2k of length. For P. So that's the case. So do you know? So only the length of purple will give you Hamiltonian. So now we forget about this minus j because it's absorbed in k. So this sum becomes negative 1. Otherwise, all the other part is you just have a plus 1 because they are aligned. Okay, they are aligned. So therefore. So that in low temperature regime, what we need to do is you just sum over the length of this purple one. That will give you negative 2k and length is. So the overall normalization is just not so important. So then the PD is the closed whatever. What did I write? Closed loop or closed path in dual lattice. Okay, so and then I call it this one is the Z high. So this is Z high temperature, and this one is Z low. Z low, and you will notice that the Z low K prime is equal to 2 times 2 sinh 2k minus n times n. Over 2. Normalization is not important actually. And times the high temperature. High temperature of K, the high temperature of K. And the K, so as you can easily see, both are actually the sum of a cross path inside a lattice. But the weight is slightly different. Weight is slightly different. Okay, weight is slightly different. So you have to equate this weight. In order to equate this weight, e to the minus 2k prime should be equal to tanh of k. So this is the equation. because here touch k is plus 2k is a weight here. So therefore, to equate, so this relation is satisfied. It needs to be satisfied. Fine. Then, so if you just massage this, if you massage this equation, what we obtain is that what we obtain. So this one will give you the following beautiful formula. Since k prime is equal to 1. So it's a good exercise to derive. This one is equivalent to this. So k and k prime are the symmetric. Fine. And then critical temperature. So from there, critical temperature is in fact the sinh 2kc is equal to 1, and the sinh is equal to, 2k. Sorry, this is 2k. Sorry, 2k and 2k prime. Sinh 2k c prime. 2k c prime. This means that the kc is equal to 1/2 log 1 plus square root 2. Fine. So that's the relation between height and temperature. So this is K is a high temperature regime, K prime is low temperature regime. If they satisfy, they have to balance it in terms of like this way. But when they are equal, you have a critical temperature, and we just keep balanced. Okay. And then, so this, the partition function of the low, the relation between low and high temperature, this is called Cramer's finality. Cramer's finality. Okay, let's continue to learn this one a bit more in the next lecture. Let's stop here. Fine. So next time, so we'll continue to learn this Cramer's finality and also this on-cycle zigzag regime. Then try to connect the Ising safety. Okay. N means the, so lattice, you have a lattice like this way. And then the side in, this is n side, you have the n side, in total the n times n side. Yes, yes. Yeah. Yeah.
What about this one? Just
this part is not equal.
Yeah. So what we have is that for minimum model, some particular charge we have
Yeah, you can consider.
And
This, if you consider this part, the OP is not closed.
yeah, this one is close. So
The OP is not closed. Then I think you have to consider infinite many the parameters. So it's not finite many. So therefore,
we should verify that C is suitable for minimum model and the harmony rotations in this region.
yeah. Otherwise, OP is not closed.
Or verify the.